So, hello everybody. We are back to our class again. So, in this class, we will discuss about propagation of electromagnetic waves in a plasma. This will be a very simplistic derivation, and usually, you know that these derivations are done in a very rigorous and very complex ways. But ultimately, the results that you will arrive in this class as well, but in a very simple way. And the mathematics that you will require will not be more than 12 standard your mathematics complexity, and you will be able to have a feel about how plasma can behave with an electromagnetic wave as it tries to propagate through that, whether it will be propagating or it will be damped. All these things will come to know. So, before we start, let us go through some basic assumptions and the kind of things that we are going to handle. So, we consider an electromagnetic wave propagating in the x direction. You just concentrate on the upper right corner image. So, I have drawn a coordinate axis and a right-handed system, and the electromagnetic wave is propagating in the x direction. So the electric and magnetic field, they are oriented as shown in the diagram. Okay, so uh, now what is doing plasma and the electromagnetic wave? There are two things: plasma and the electromagnetic wave. Plasma, what is there? They are charged particles, and electromagnetic wave that propagates with its own speed. Okay, and you know that in space, this electromagnetic wave propagates with the speed of light c, and this E and B are related with relation kind of that is shown in the right side, that is C is equal to E by B. So, if you consider the speed of light, that is something very high. You know, 3 into 10 to the power 8 meter per second, that is the speed of light in space with which the photons move. But inside the plasma, the particles are moving much slower than that. So this thing you should remember actually. Inside plasma, when the electromagnetic wave when we are treating that electromagnetic wave inside plasma, we are basically considering two types of velocity. One is speed of the electromagnetic wave, so that is very high, and the other one is the speed of the particles, which is pretty low. So the electromagnetic wave is basically acting on the charged particles. So here, as you know that because the electromagnetic wave is electrons can respond to this electromagnetic wave very fast. So basically, they will be trying to respond to this primarily. Now, the equation of motion of a charged particle q, you can write in this coordinate system. So, x coordinate, y coordinate, and z coordinate, you can write the same thing, because what we have used on the right hand side is the Lorentz force qe plus v cross b, right? So, dy dt and dx dt, they are the velocity components. They are the velocity components of the charged particles. And you know that QE is there, which is when you are considering the motion in the y direction, and in x direction there is nothing. So only v cross b terms, that v dy dt term is coming, that is contributing over here, and y component, the dx dt b into dx dt is contributing over there, and in the z direction, so there is nothing. So what we can do now, that let us assume that the electric field is moving like E equal to 0 cos omega t. We can always assume like that, and we can approximate the second equation on the first white box. The second equation, we can approximate that as, you take the E out from the bracket, and on the right side, what we get is written on the lowermost this thing equation. That is q by m. If you take it out, then it is inside the bracket. You are getting 1 left, and then b by e dx dt. As I told you that dx dt is the velocity of the charged particles, and e by b will give you the c, the speed of light or speed of electromagnetic wave. So that is quite high. So when you divide dx dt by c, that can be neglected or with respect to 1. And what you get essentially that equation as q e0 cos omega t divided by m. So if you integrate it over, then you get a dy dt equal to q e0 by m omega sin omega t. And if you use this, so then what you get actually, j, that is the velocity in the y direction, and that is linked with the electromagnetic wave frequency and the strength of the electromagnetic field, of course. Then j is equal to the current density. You know that it is related with the velocity as nev, right? So v is the velocity. So here what you are getting, ne dy dt. Now what happens, this is constituting a current density, and it is coming like that. If we put the value of dy dt, then it is coming to be ne q0 by m omega sin omega t. So if we solve this and we write that j is equal to sigma e is equal to sigma e0 cos omega t, then what we get out of this is that sigma is equal to, sigma corresponds to basically minus j n square by m omega when you are going for this electrons. Actually, basically these electrons are contributing, and you can write that sigma is equal to minus j n square by m omega. If you compare these two, and what you better actually, E equal to 0 j j omega t if you write, and if you compare these two, then you will be getting a better expression for this much easier way to get this sigma is equal to minus j n square by m omega. So what you are getting, a complex relationship for this conductivity, electrical conductivity. Now what we are getting over here, the Maxwell's equation, curl equal to minus del v t, which is always valid over here, and then also curl h is equal to j plus epsilon del E del t, the another Maxwell's equation. Now if you put this value of j is equal to sigma e, and this I have actually interchangeably used epsilon and epsilon 0, so you should put them in a convenient manner. So what you are getting over here is sigma e plus sigma epsilon 0 del E del t, and what we got that delta E delta t, if you consider E equal to 0 j omega t, then if you apply that, then you can finally result into that the second row equation. What you are getting, curl h is equal to j sigma epsilon 0 into E into 1 minus n square by m omega square into epsilon 0. Now what we will do? We will take a curl of the first equation, that is the upper right corner equation, curl equal to minus del v del t equal to minus j omega mu 0 into h. So if you take a curl of that, then curl of E, it is coming to be minus j omega 0 into curl h. Again curl h, whatever we are getting in the your right lower box, you can see that curl h is equal to j omega epsilon 0 e into 1 minus n square by m omega square epsilon 0. So if we put that value in this, then we finally get the expression what is written on the lower right box. And there you are getting that curl of B is equal to minus j omega mu 0 into curl h, and you have put the value of curl h. Then if you expand the left hand side, curl E equal to gradient of divergence E minus del square E, then you get whatever the expression you are getting. Now there is one thing. Now whether divergence E equal to rho by epsilon 0, whether we can take the rho equal to 0 over here, because if we take that rho equal to 0, then this expression becomes extremely simple. And whether we can take rho equal to 0 for simplification in some cases. Now, if we are considering some propagation of electromagnetic waves, where your this wavelength of the plasma is much greater than the your Debye length, then for all practical purpose, the rho can be considered to be 0, and we can just eliminate the term divergence C equal to 0. We can just put for that kind of situation, and then we will get actually del square E is equal to gamma square E, where gamma square is equal to, given that 1 minus your minus omega square by c square into 1 minus omega c square by omega square, and we can write that as alpha plus jk. So this term, this gamma square is equal to alpha plus jk. If we want to write that, then there will be solution when gamma square greater than 0, gamma square less than 0, and gamma square equal to 0. And for these cases, the solution that you will get equal to C1 e to the power gamma x plus C2 to the power minus gamma x, and E is equal to, in the second case, e to the power alpha x into C3 cos kx plus C4 sin kx, and in the third case, gamma square is C5x plus C6. So they are all constants, C1 to C6. Now if omega is greater than omega p, then what you are getting, this gamma is equal to pure imaginary. You see that gamma square is equal to omega is greater than omega p. So then the right hand side is involving all squares, and it is negative, purely negative. So in that case, gamma becomes purely imaginary. So if omega is greater than omega t, gamma becomes purely imaginary, and the wave propagates with wave vector k. And if omega is less than omega p, then gamma is purely real. You see that. Then omega less than omega p, so that term inside the bracket in the topmost equation, you get the gamma square is purely positive, and then gamma is real. And in that case, actually, if gamma is real, then the wave doesn't propagate, it gets damped. So you get an expression for your propagation of the wave velocity, that is the phase velocity, Vp is equal to omega by k, and that becomes omega by square root of 1 minus omega p square by omega square, and of course omega by c is multiplied with that. So finally what you get, Vp is equal to the phase velocity of the wave is equal to c by square root of 1 minus omega p square by omega square. So phase velocity, once you get, you know that you can get the refractive index of the media. So that comes to be mu is equal to c by Vp, and it is coming to be square root of 1 minus omega p square by omega square. So what we now find that if an electromagnetic wave tries to propagate through a plasma, then if omega is greater than omega p, then the wave can propagate with a wave vector k and speed as omega by k, that is the phase velocity, that equal to c by square root of omega p square by omega square, and it offers a refractive index for that electromagnetic wave as square root of 1 minus omega p square by omega square. So it is very much related with the plasma oscillation frequency of the plasma that you have created, and that again depends on the number of particles per meter cube that is present in that medium. So depending on the kind of number density, a plasma can diffract plasma can actually refract a wave in different direction. So an electromagnetic wave, when you launch, it will bend exactly like the light rays that get refracted as it goes from your through a media of certain refractive index, and the velocity with which the wave will propagate, this phase velocity, that is again depending on the plasma oscillation frequency of that medium. So this is a very simple derivation for this how an electromagnetic wave can propagate through a plasma. Whether it will propagate or not, that depends on the plasma oscillation frequency and the frequency of the wave. If the frequency of the wave is more than the plasma oscillation frequency, then the wave will propagate through the media, and it will not propagate in a straight way. It will propagate like a wave when it propagates through a refracting media, so that path will be bent in certain direction depending on the kind of media it is facing. So now I will come to the concept of temperature. So already I am telling you different types of temperature in the plasma from the beginning, without introducing exactly what plasma temperature is. Now when we talk about temperature, we never thought of different kind of temperature. Suppose I want to say that temperature of this room is this much, or this object is at this temperature, then we never think of different kind of temperatures inside that room or for that object. We always consider that is the same actually, the temperature that is reigning over there. But when we come to plasma, different types of temperature exist within the same plasma. That I will just try to tell you in this lecture. So why such different types of temperature exist inside plasma? You can simply understand from the way we generate a plasma and the constituents that are there inside the plasma. You know that most of the times we generate the plasma by heating, and the heat comes through electrical discharge usually. So we are using some electric field to generate the plasma. We are energizing the plasma, trying to collide with the neutrals and strip out further electrons, and finally producing an ensemble of electrons, ions and neutrals, which is actually called plasma. Now when I am doing so, it is very obvious that those electrons which are present inside the media, they will respond to the electric field very fast, and once they are energized, they will move. When they are applied, when they are getting exposed to that electric field, they will get accelerated and they will collide with the other particles. Now electrons will respond to the electric field and they will get energized and they will collide with the other particles. But electrons are very light. So when a very light particle undergoes elastic collision with a very heavy particle, it loses little of its energy. Whereas when two objects of identical mass collides with each other, they almost exchange their energy. Like two bodies of same mass, if one is moving with speed v0 and the other is at rest, after collision the first one comes to rest and the other one starts to move with velocity v0. So this we have studied in our 12th standard textbooks. So there the exchange of energy is complete. But if a very light particle collides with the other very heavy object, it almost loses no energy and it stays at its original value actually. So through collision, electrons exchange very little of their energy with the other particles. But if there are a huge number of such collisions per second, then it may be possible through collision only. Even though the your energy transfer is less, they can equilibrate. Now, that exactly what happens in case of thermal plasma. So what I am trying to say is that electrons gain energy from the field very quickly, they lose very little of them. On the other hand, these bulky ions, they also get acted upon by the electric field, but because of their heavy mass, they cannot move very quickly with that field, and they get energy but not that much. Mainly the energy comes through the collision from the electrons because they can respond very fast and they are very light. On the other hand, if they are neutrals, then they will not respond to the electric field at all. So how they will increase their energy? So they can increase their energy, of course, through collision with the neutrals and with collisions with the ions, which are actually can respond to the electric field. And in those cases, the energy transfer will be very good because they are having almost equal masses, these heavy particles. So it is obvious that electrons will be acted upon by the electric field and they can gain energy very fast and they will be having the highest energy. On the other hand, the ions, they are getting energy from the through the collisions with the electrons and they also can respond to the electric field and get energized. So they will be having the second highest temperature inside a plasma, and the neutrals, which do not respond to the electric field at all, which are bulky and which can get energy through collisions from the electrons and ions, they will be having the lowest energy. So in a plasma, we can easily understand that the electrons will be having the highest energy, ions will be the second highest, and the neutrals will have the lowest energy. But as far as energy is concerned, you know that these neutrals and the ions, because they are so large in number, they will collide with each other and almost come to a level of energy which are almost nearly same. But electrons, but ions may have the opportunity to have a higher energy. So all this basically depends on the situation. And as I told you, in a non-thermal plasma, electrons have always the highest energy and much higher compared to the neutrals. Whereas in thermal plasma, large number of collisions per second equilibrates them almost at the same temperature. That is the electron temperature, ion temperature and heavy species temperature, they are the same. So inside a plasma, there is high probability that multiple species stays at multiple temperature. I have just given here one example that we know that in an assembly of gas particles, it is the Maxwell-Boltzmann distribution which describes their speed distribution. And you know that average velocity we have calculated many times in our textbooks in earlier classes in BSc or even higher secondary, that average velocity can be computed as 1 by n integral of c and delta n. Then that basically integrates over the all particles, and when you divide by 1 by n, then you just get it averaged out, and that value comes to be root over 8 kT by m pi. Now if you calculate the average energy, half mCv square, it is coming to, we see that it is 4 by pi into kT. So if these charged particles, these neutrals and these electrons, they are having different energies, then you can connect each energy to a different temperature through E of the order of kT, and that temperature will characterize each species inside the plasma. So inside a plasma, we can easily describe each species with a different temperature. So usually what we do, actually we describe the electrons with electron temperature, heavy species with temperature TH, and these are basically two temperature model mostly people follows, and there are models with multiple temperature, but they are difficult to handle because you need to consider each species having a different temperature. But this two temperature model, that is electrons are having temperature Te and ions are having temperature Th, that can well describe a plasma for most of the practical purposes. So with this actually I stop the concept of this plasma temperature, and I introduce you to another very important plasma aspect, that is plasma equilibrium. You know that inside plasma, what is going on? There are different kinds of equilibrium exist inside plasma. One is just physical movement of the particles. They are charged particles like electrons, ions, and then heavy species. Then, through the collision with the electrons, their excitation of the atoms and the electrons get excited to different energy levels. Then through collision you can have ionization, this thermal ionization, you already know the Sa ionization equation, and there is radiation. You know that it's plasma. When we are in this room, we see that the tube light is radiating light, and they are radiating light because they are excited through the discharge, the particles inside, and they are radiating. So when we are having a high temperature object like plasma, maybe the electron temperature is high or both of them, electron and heavy species temperature both are high, excitation takes place, movement takes place, ionization takes place, and radiation comes out. There is certain situation when all these are in equilibrium. So in this slide I am showing that kinetic equilibrium, when it is maintained among the electrons, they maintain a Boltzmann distribution of speed, Maxwell-Boltzmann distribution, and you see that they are equilibrated. That equilibrium is hold for a certain temperature Te, and that is appearing in the exponent of that first equation. Similarly, the heavy species, they are colliding among each other and they are maintaining equilibrium, but that equilibrium distribution is characterized by a different temperature, and that temperature is Th. Similarly, the electrons are colliding with the atoms and the atoms are colliding with other atoms, and they are getting excited, and in that actually you are getting an excitation equilibrium as presented in the third equation. Similarly, for ionization, you will get a temperature where this expression holds, and radiation, you all know that there are black body radiation when there is radiation equilibrium holds, and that is characterized by other temperature Trad. In plasma, when all these temperatures are equal, that is electron temperature is equal to heavy species temperature is equal to excitation temperature is equal to ionization temperature is equal to radiation temperature, we say that the plasma is existing in complete thermodynamic equilibrium. And when rest of the temperatures are equal, but that is not same as the radiation temperature, we say that it is in local thermodynamic equilibrium. But when this LT kind of expression holds only for higher lying states in an atom, but not for the lower lying states, then we call that kind of plasma often encountered in high pressure discharges like arcs at partial local thermodynamic equilibrium. So I stop here, and in the next class basically we will go for the collisions in plasma and what are the different collision scenario. That is very important to understand basically how a plasma should behave. So I stop here, meet you in the next class.